Hi, this is Moser with a pep talk on overcoming friction. So, up till now, we've done problems where we used the coefficients of static friction or kinetic friction in situations where objects were either not moving yet or moving at constant velocity. Now, we're going to see what happens when we have an object that's accelerating. Oh boy. The coefficients of friction then, along with the sums of forces on each axis, gives us a whole arsenal of tools that we can use to find either the acceleration or the mass of an object. So, I will instruct you to walk through sample problem 4D on page 146 in your book, and I'm going to go through a sample problem with you that's sort of, well, it's off an old quiz. Okay, here we go. Alright, we have an object sitting on a surface which is sloped at 30 degrees. The object has a mass of 15.0 kilograms and 80 newtons of force is being applied directly up the slope. The coefficient of friction between the object and the surface is 0.222. So the question is, what kind of acceleration can we achieve here? Well, the first thing to do, of course, is to map out all of the forces so that you can do sums of forces on this. Because the way this is going to work, well, really you're going to have 4 different equations that you can use as tools for substitutions. Oh boy, let's go. Okay, so I've mapped out all my forces, and we can see that on the y-axis I have just normal force. I've got the force of gravity on the y-axis, but on the x-axis I actually show 3 forces. I have the force of gravity on the x, I have the applied force on the x, and I have the force of static friction. Why is the force of static friction pointing down slope? Because this thing, we believe, is being moved up slope. So the motion is upslope, therefore the force of static friction opposes motion. Alright. The first place to start with any problem like this is listing your sums of forces on each axis. Okay, I'm going to start with the y-axis because it's fairly straightforward. We know this thing is not moving up into the air or dropping down through the surface, so sum of forces on the y-axis is equal to 0, and the only forces on the y are the normal force and the force of gravity on the y. Therefore, Fn is equal to Fgy. Therefore, Fn is equal to mass gravity cosine theta. I'm just going to leave that there. I'm probably going to have to use it as part of a substitution. Now this is where it gets a little bit trickier than the problems we've dealt with before. In this case, we know that there is some acceleration on the x-axis. Therefore, the sum of forces on the x-axis is not equal to 0. In fact, the sum of forces on the x-axis is where we're going to find our net force, which means that it's equal to what? That's right, mass times acceleration. Okay, going to set that aside because we also know that the sum of forces on the x-axis is equal to the applied force minus the force of gravity on the x minus the force of kinetic friction. I had a mistake earlier and listed that as the force of static friction. I've corrected it now. Okay, so that means that the mass acceleration is equal to the force applied minus the force of gravity on the x minus the force of kinetic friction. Oh boy, we're not given a whole lot here. Alright, so I've rewritten that to show that ma equals F applied minus mg sine theta minus Fk. I've got one more equation, and that is that mu k equals Fk over Fn. Well, it's unlikely that I'm going to create an expression for Fk using all those other variables, and in fact that would be really stupid because the thing I want to know is the acceleration of the object. What's much more likely is that I'll create an expression using that equation for the coefficient of kinetic friction, like this, stating that mu k Fn equals Fk. And since I have everything that I would need to calculate Fn, and I have mu k, it's much more likely that I would use this expression and plug it back into the expression that takes place on the x-axis, relating Fk, Fgx, and F applied back to Ma. Since I know that I'm going to use this equation because I'm looking for acceleration, and I have mass, I have applied force, I have mass, gravity, and I have an expression for Fk, I'm going to go ahead and substitute this back in for Fk. So I have my first iteration of this expression right here. Now, because I don't have Fn, but I have an expression for Fn, you see what's coming next. Okay, Ma equals F applied minus mg sine theta minus mu k mg sine, or cosine theta. Whew, there's only one thing left to do to solve for mass, and this one's pretty easy. I'm going to divide both sides, to solve for acceleration rather. I'm going to divide both sides by mass. That moves mass from the side with acceleration, isolates acceleration, and gives me something I can plug into. Okay, so with all of our values plugged in, divided by 15.0 kilograms, we have acceleration is equal to 80 newtons minus the quantity, 15.0 kilograms times 9.81 meters per second squared times sine of 30, minus, brackets could be on either side, 0.222 times 15 kilograms times 9.81 meters per second squared times cosine of 30, all divided by 15 kilograms. And our final answer is... how embarrassing. Well, when I try to change numbers on the fly, this is what happens. If you're only pushing with 80 newtons of force, you're not going to push this box up the hill. So we're going to change the applied force to 115 newtons. That's better. Cut that. 115 newtons. Okay, now go ahead. Get your raw number. Alright, are you ready? Well, the raw number that I'm getting is 0.875619922 on and on meters per second squared. In other words, not much of an acceleration at all. You really should be pushing harder. How many sig figs do we have? 3. So final answer would be acceleration equal to 0.876. 0.876 meters per second squared. Tragic. Anyway, you get a sense of how these go. They tend to be a little bit more involved than what we've done in the past. You really need to prove everything using your sums of forces. So, prove your Fn, prove your x sum of forces on the x. Use those 3 equations to substitute back into one another. Let's go through a list of cautions. Always start with your sum of forces. Make sure you're accounting, I should say, free body diagram. Make sure you've got a free body diagram. Make sure you have all your sums of forces. Have you got every force mentioned? Do you have those forces accounted for properly? Have you broken down any forces that are actually vectors to start with? And above all, if you can remember this, and after the mini forces in friction lab, you shouldn't be able to forget it. Normal force is not always just equal to Fg. Okay, that's it. All of the 4D practice is assigned, and when I see you later, we will get you the 4D worksheets. So use today and tomorrow to catch up on 4C and to get started on 4D. All right, have a good day.